Okay, good evening. So we will continue with the place we stopped last week. So last week we have covered part one and part two. So currently we are looking at amplitude modulations. So in part one we have seen how the modulation, what is amplitude modulation, and how the modulation is happening. And in part two we have seen about amplitude modulation modulator and also demodulators, and today we will enter into another part of modulation. Okay, so in modulation called double sideband full carrier. Okay, so as you can see, so the abbreviation is so double, so DSBFC. Okay, so double sideband SB sideband full carrier. Okay, so what is double sideband full carrier? So if you see a signal when it's modulated, it will be in this form. Okay, so in between, this is the carrier signal. So we will have a lower band, so which is FC minus FM, and also upper band, which is FC plus FM. So these three components are there in the modulation. Okay, so we have some read up. So in the process of amplitude modulation, the modulated wave consists of carrier wave and two sideband. So one carrier wave and two sidebands, okay, lower and upper. The modulated wave has the information only in the sideband. Okay, so we need to know. So carrier is not holding any information. So information are always in the lower sideband and also upper sideband. Okay, sideband is nothing but a band of frequencies. Okay, so here you have different variants of frequency. So in between you are keeping your informations. Okay, so containing power. So when it is having differences in the frequency, so you can get some power, so which are lower and higher frequency of the carrier frequency. Okay, so this side it will be lower and this side will be upper. So the transmission of a signal which contains a carrier along with two sideband can be termed as double sideband full carrier. Okay, so what is double sideband full carrier? So these three components. So it must have lower sideband, it must have carrier, and also upper sideband. So if your modulator signal has all three, so we call it as double sideband full carrier. So because it's full, okay, full. So all the components are there. Okay, or short form we can call it as a DSBFC. So double sideband, okay, full carrier. So it is plotted as shown in the following figure. So this figure, however, such a transmission is inefficient. So meaning, so even though it has all the components, inefficient means it's wasteful. So we will see why it's wasteful. Okay, because two-thirds of the power is being wasted in the carrier, which carries no information. Okay, as I say last time, if you want to move from Perlis to Kuala Lumpur by car, so the car is the carrier. Okay, so the car is what holding the energy. Okay, all the energy, the petrol or diesel or whatever. So it is consuming and it is taking most of the power which is being wasted in the process of sending the information. Okay, and the car cannot carry any information. We are the uh, information, so the information is with us, it's not with the car. So the car is just the mode of transportation. Okay, similarly the carrier is only for transportation, but it is consuming two-thirds of the power of the signal. Okay, so that's why we call it as a inefficient. Okay, so in order uh, to make it efficient, so there are few methods are there, so which we can see. So if the carrier is suppressed and the safe power is distributed to the two sideband, then such process is called double sideband suppressed carrier. Earlier full carrier. So now what we planning to do, because we already know that the carrier is having all two-thirds of the power and is wasteful. So what we try to do, we have a certain kind of circuit which can suppress. Suppress meaning this FC becomes 0. So we suppress, and the power is distributed to lower sideband also and upper sideband. So meaning in this component, double sideband suppressed carrier, or we call it as DSBSC. So you only have two components. Okay, this component becomes 0, so it's not existing. So you only have lower sideband and upper sideband. Okay, so carrier is suppressed and sidebands are allowed for transmission. Okay, so it's supposed to increase a little the efficiency of the transmission. Okay, so we see some mathematical expressions, okay, just for your understanding. So let us consider the same mathematical expression. So like the previous part 1 and part 2. So we have seen a similar kind of formulas. Okay, for modulating signal or the information signal, so we call it as MT. So AM cos 2 pi FMT. So this is the standard form. Okay, standard form. And carrier signal, we always call it as a CT. So C for carrier, M for modulating. So CT equals to AC cos 2 pi FCT. Okay, so mathematically we can represent the equation of DSBSC. Okay, so there's a surprise one. Okay, as the product of modulating. So we know in order to get the AM wave, you need to times these two. Okay, and it is called as ST. Okay, the signal. So MT times with CT. Okay, so then these two, if you times, you will get the signal like this. Okay, the formula AM AC cos 2 pi FMT cos 2 pi FCT. Okay, so if you don't know what are the components, you can refer to the previous lectures, previous parts. Okay, then we can calculate the bandwidth. So this already we learned last week. So bandwidth of DSBSC, so double sideband suppressed carrier. Okay, suppressed carrier with, we know the formula of bandwidth. Bandwidth is F max minus F min. So based on our previous slides. Okay, so consider the formula for the modulated wave. So ST. Okay, so if you have a trigonometric expansion, so if you further expand this, so it will be changed to this form. Okay, so AM AC over 2 cos 2 pi FC plus FMT plus AM AC over 2 cos 2 pi FC minus FMT. So it's only having two components. No, so it's a upper sideband and also lower sideband. So the DSBSC modulated wave has only two frequency. So the maximum and minimum frequency are FC plus M. Okay, so this is the maximum, and the minimum frequency is FC minus FM. Okay, so we can get this. Okay, so you substitute in the bandwidth equation. So earlier, so this equation. So when you replace this, so you can get FC plus FM minus FC minus FM. Okay, so once you solve, so we can get the bandwidth equals to 2 times of modulated frequency. Okay, FM. Okay, that's the bandwidth of DSBSC wave is same as the AM wave, and it is equals to twice the frequency of the modulating signal. So you find the frequency of the modulating signal, you times with 2 in order to get your bandwidth. Okay, so usually we will ask to calculate F max, F mean, so bandwidth, and we also can be asked to calculate the power. Okay, so the power for DSBSC. Okay, so this is the modulated signal earlier. So power of DSBSC wave is equal to sum of power of upper band, upper sideband and lower sideband, because it's only having two components. So no carrier. Okay, so power total equals to PUSB upper sideband power plus lower sideband power. Okay, so if you plus both, you will get the total power. Okay, so we know the standard formula for power of cos signal. So this is from the previous slide, so you can refer to the previous slides. P equals to Vrms square over R, or Vm square root of 2 square divided by R. Okay, so you replace the information so you can calculate the power. Okay, so from here we can calculate the power, upper sideband power. Okay, so this is they already derived in the previous slides, so you can refer. So you no need to derive again. You can just take the same formula and put it here. Okay, so the final, so upper sideband power is Am square AC square over 8R. So if you don't know where it is, so I can show you. Uh, so in these slides, so you can see slide number 17, okay, and 16. So you can refer to this slide to refresh yourself. Okay, so similarly we can get the lower sideband power. Okay, since both are the same, so lower sideband powers, so this you please change to PLSB. Okay, PLSB. So power, lower sideband power equals to the same like power USB, AM square AC square over 8R. Now let us add these two sideband because we want to find the total power. So according to this equation, upper sideband power plus lower sideband power. Okay, upper sideband power we already calculated. So lower sideband, so please change here. So it's the same. So you are getting this or 2 times of this. Okay, so you just cancel. So you can get AM square AC square over 4R. So that is the total power for double sideband suppressed carrier. Okay, so the power required for transmitting DSBSC wave is equals to power of both the segments. Okay, so you power both segments. Okay, so that is the DSBSC. Okay, so we also have a DSBSC modulator. Okay, so because the AM modulator that we have studied last week, it consists of all the components. Okay, all the components, upper, lower sideband, carrier, and also upper sideband. But in DSBSC modulator, so it's only having two sideband, no carrier. Okay, so in this chapter, let us discuss about the modulators which generate DSBSC wave. So there are two types of modulators which can generate this kind of signal, DSBSC wave. So we call it as a balanced modulator and also a ring modulator. So we will see both shortly. Okay, so this is balanced modulator. So from the name we know it must have a balancing element. So you have two types of modulating signal we are giving. So this is the positive signal. So you have two AM modulators in this case, and in between you have a carrier, so controlled by the local oscillators. Here you are giving the positive signal, and here you are giving the same signal but in negative form. So you're getting both. So once it go through here, so you will get one output S1T. So from here you will get S2T. So you combine together to form ST. Okay, so that's the reason why we call it as a balance. So because it's having both, and the accumulator is actually the adder is actually balancing the signal and modulating the signal. Okay, so it consists of two identical AM modulators. So AM modulator 1 and AM modulator 2 arranged in balanced configuration to suppress the carrier signal. Okay, so our aim is to suppress. So we need to have an individual, then after that we are suppressing here. Okay, so the upper AM modulator, so this is your upper AM modulator. The input is positive of modulating signal, and lower is a negative modulating signal. And the carrier input is AC cos 2 pi FCT. Okay, so equation 1. Okay, so output of upper AM modulator is S1T. So S1T is AC. So you can see the only difference is here it will be plus, here will be minus, because here minus signal. Okay, negative signal. Okay, so you can get equation 2 for upper modulating, which is plus, and lower modulating you can get 1 minus Ka mt cos 2 pi fct. Okay, so your output of these two, so you can get equation 2 and equation 3. So you already, once you get S1T and S2T, so you will combine together. Okay, so that is equation. So and DSBSC wave using summer block, so you are joining together. Okay, so this is positive signal, this is negative signal. Okay, so you will get S1T minus S2T because you are finding the difference. Okay, so it's actually S1T plus minus S2T. So it become minus. Okay, so this is your equation. So once you solve, you replace these equations, this equation and this equation in this formula. Okay, then at the end, once you solve it, you can get equation 5. Okay, so equation 5, 2AC KAMT cos 2 pi FCT. Okay, so that is your DSBSC. Okay, so if you compare with the standard DSBSC equation, okay, so try to compare with the standard equation. So standard equation is AC KAMT cos 2 pi FCT. So if you see the behind part, all the same. Okay, only the front part is different. So you have 2 here. If compared to this, so you have additional 2, and also so Ka is the constant, is the scaling factor. So compare equation 5 and also equation 3. So to find the scaling factor, so the scaling factor is 2 times of Ka. So 2 Ka. Okay, so you already know the Ka. Then after that, so you can try to pass the signal and also demodulate it. Okay, so that is your balance modulator. Okay, so there are another type of modulator, we call it as a ring modulator. Okay, so it's basically the difference between the modulators are the constructions. Okay, so some place it's having some interference interface, so this point is connecting to this point. So when you change this kind of setup, so it can give you a different variability to your modulator. So this type we call it as a ring modulator. Okay, so in this ring modulator, so there are 4 diodes, so D1, D2, D3 and D4. Okay, so you have 2 transformers to send and also to compress. Okay, so in this diagram, the 4 diode D1, D2, D3 and D4 are connected in the ring structure. So this is a ring structure. Okay, so maybe the actual one will look more like a ring structure. Okay, so this is only the circuit. Okay, hence the modulator is called a ring modulator. Okay, so 2 center tap transformers are used in this diagram. So you have 1 transformer and 2 transformer. The message signal MT is applied to the input transformer. So message signal is entering here, so it will transform and it will be sent to the middle circuit. The carrier signal CT is applied between the 2 center tap. So there are CT here, so between these two. So you are taking from here to here. So this is your carrier signal. So you are sending the signal from here to this side. Okay, so in order for you to get, so normally waveform it will have a positive. So like if you see the sine wave, it will go up, then it will go down. So it will be a positive side. Then it will go to the negative. So it will go down, then go up. So when you are playing around with these diodes, so you can get a positive half signal and also negative half signal. Okay, so what is positive half signal? So sorry, positive half cycle of the carrier. So you on D1 and D3. so you switch on, and D2 and D4 are switch off. Okay, so D1 and D3. So you on this and this. So these two you off. So the signal will go here and the signal will go here. So it will find the comparison and it will send. Okay, so when you do that, so the signal will not cross over. So it will just follow this side. Okay, so this side it will follow D1. So this side it will follow D3. Okay, so no crossing. Okay, so what it will do, so it will have so the message signal is multiplied by plus 1, so it will become like a positive. So in order for you to get negative half cycle of the carrier, so D2 and D4 are switched on and other two diodes D1 and D3 are switched off. Okay, so D1 and D3 switch off, so you only have D2 and D4. Okay, so the signal will go here. So then it will cross this side. Okay, so it will cross. And then it might have, because diode only allowing in one direction, so it can have a crossover in order to create a negative signal. Okay. So in this case, the message signal is multiplied by -1. So the result, it become under 80 degrees phase shift. So that's why the signal is going down and it's a negative half signal. Okay, from the analysis above, we can say that the four diodes D1, D2, D3, and D4 are controlled by carrier signal. Okay, so you have a carrier signal, so it will determine when it need to give this side, when it need to give this side. Okay, so that it will on the respective diodes. Okay, so it's controlled by the carrier signal. So if the carrier is a square wave, then we are applying a Fourier series representation. So the formula will be like this for the carrier signal. Okay, so when you substitute, okay, so the product of carrier signal and also message signal, okay, in order to get a modulated wave, so you will get the formula like this. Okay, so this is the formula for DSBSC wave, double sideband suppressed carrier wave. Okay, the above equation represent DSBSC wave, which is obtained at the output transformer of the ring modulator. So you are getting this at this, so output transformer. Okay, so this is your SD, which will be transmitted. Okay, so DSBSC modulators are also called the product modulators, as they produce the output, which is the product of two input signal. Okay, so you're giving two input signal. Okay, so you're giving the signal, and you have a carrier wave, so which will determine which side of the signal will go. Then it will be added, and also it will be times. Okay, product, because it's product. So earlier we saw addition, so here is multiplication. Okay, in order to form your amplitude modulated wave. Okay, so then there we have another type of uh, system. We call it as a single sideband suppressed carrier, so SSBSC. Okay, so earlier we saw the full carrier, double sideband DSB full carrier. Full carrier, it has three components. So it has a lower sideband carrier and also upper sideband. So then we saw double sideband suppressed carrier, so which suppress the middle part, okay, the carrier. So only having lower sideband and also upper sideband. Now in single sideband suppressed carrier, so you are suppressing lower sideband and also carrier. So only one upper sideband is available. So meaning three different system. So three things are varying. Okay, so you just need to understand. So what's the differences between the suppressed carriers and also full carriers? Okay, Okay, so in the previous slide, we have discussed double sideband suppressed carrier modulation and demodulation. The DSBSC modulator signal has two sideband. Since the two sideband carry the same information, there is no need to transmit both sideband. So we can eliminate one sideband. So what they are saying. So earlier, yeah, in this part, okay. So in this part, so you have a lower sideband and also upper sideband. But in a single sideband suppressed carrier, so they are saying so the information here in lower sideband and upper sideband are the same. So why you need to send two times? Okay, same information. Okay, so here let's say the information is uh, either. So here also either. So you only want to send one message, but you need to send two times. So what happened in single sideband suppressed carrier? So you cancel the lower sideband and you also cancel the carrier. So you only maintain upper sideband. Okay. So the process of suppressing one of the sideband along with the carrier and transmitting a single sideband is called single sideband suppressed carrier system, or simply SSBSC. It is plotted as shown in the figure. Okay, so in the figure, the carrier and the lower sideband are suppressed, hence the upper sideband is used for transmission. Similarly, we can suppress the carrier and upper sideband while transmitting the lower sideband. Okay, so since both are having the same information, so you can decide you want to suppress the lower sideband or upper sideband. So if you want to suppress the upper sideband, so you just suppress the carrier and also upper sideband, only allowing lower sideband. Okay, so in single sideband suppressed carrier, you only allowing either one of the sidebands. Okay, so this SSBSC system which transmit the single sideband as I power. Okay, so because all the powers are earlier distributed to two band, now it's only distributed to upper sideband because the other two are not available. Uh, so meaning like here, let's say if I give an example of money, so let's say you have 200 ringgit. So earlier you give 100 to the lower sideband and 100 ringgit for upper sideband. So now you already eliminate these two. So you have 200. So upper sideband using the 200. So that's why it will have a more power allocated for this sideband that is carrying the information. Okay, some mathematical. Okay, so we can represent. So this is the signal from the previous slide for the upper sideband. Okay, I'm not deriving again. Okay, so the for upper sideband, and this is the signal for lower sideband. And bandwidth we can calculate. So earlier we have seen, so the bandwidth is 2 FM. Okay, for both sidebands. But here since it's only single sideband, so 2 FM divided by 2. Okay, so the bandwidth of SSBSC modulator wave is FM. Okay, so divide by 2. Okay, so consider, so to calculate the power. Okay, so earlier for the power, you add upper sideband power, you add with lower sideband power. But here since it's only having one sideband, so the power is allocated to that particular sideband. So it can be upper sideband or it can be a lower sideband, depend on which one you choose. Okay, so same formulas apply here. Okay, so earlier we have seen PUSB is AM square AC square over 8R. So all these are already in the previous slide, so you can refer back. And here they say the upper sideband power same as the lower sideband power. So the values are the same. Okay, so the power of SSBSC wave, so P total equals to PUSB equals to PLSB equals to AM square AC square over 8R. Okay, so all this information, so depends on the question. So if the question is giving uh, either these three systems. Okay, so double sideband full carrier, or double sideband suppressed carrier, or single sideband suppressed carrier. So we have three system. Three system have three different functions. So all all these systems are available for you to increase the efficiency of your modulated signal. So you want to utilize fully. So as I said earlier, so if you only have a budget of 200, so you want to use it efficiently. So you don't want to waste. So you don't want to, out of 200, so 180 ringgit go just for the petrol. So it's not efficient. So we try to suppress the unwanted signal so that we don't need avoid wastage in the transmission. Okay, so that's the function of this. Okay, so advantage and disadvantage of single sideband suppressed carrier. So the advantage bandwidth or spectrum space occupied is lesser than AM and DSBSC wave. Okay, so you have more bandwidth. Okay, the bandwidth lesser means so it's using lesser bandwidth. So meaning in terms of money, so 200. So maybe it's only using 20 ringgit. So you have more resources. So it's you only using a lesser amount. Okay, that's one advantage. Transmission of more number of signal is allowed. Okay, so when you have, if your budget already reduced to 20 ringgit, is only you have 200, so you have 180 ringgit more. So you can send another 9 signal. So transmission of more number of signal is allowed. So it can the power or the distribution can be used to transmit more signal. So power is saved. Okay, so of course, like if you only use a very limited when not many components are involved, so the power can be saved. Okay, so high power signal can be transmitted. Okay, so if like the money example, if one budget to the budget needed to send one signal is 20 ringgit, so you can send high power signal, so maybe 50 ringgit worth of signal. So because you have more budget, so you can send high power signal, you can transmit. So less amount of noise is present because we already suppress most of the signal, because the noise is available in the environment and also in the signal that you are sending. So when you already suppress most of the component, only one out of three, you now only left one. So less amount of noise is present. Okay, so signal fading is less likely to occur. So signal fading will happen maybe after you travel for certain distance. Okay, similar like your car. So after you travel for a certain distance, you need to fuel up. Okay, so signal fading can happen in the transmission line, especially because of frictions, because of additional noise. So it can hinder and it can cause a signal fading. So when you already suppress the repetitive signals, so signal fading is less likely to occur. Okay, so but it also has some disadvantages. So the generation and detection of SSBSC wave is complex process. So earlier we have seen how the ring modulator, so the construction of the ring modulator, so already it looked like a bit like complex. So when you are using a single sideband, it will be more complex, more diode will be used, or more electronics will be used in order to generate the signal. So signal generation can be complex. So in terms of business, when the process is complex, more cost needed, more cost will be needed to generate the signal. Okay, and also detection. Okay, so here you already somehow you generate and you already compress and you are sending the signal. So detection in the demodulator side, in the receiving side. So you must have a better detection system to understand what message is sent. So the overall the system will become more complex, and the quality of the signal gets affected unless the SSB transmitter and receiver has an excellent frequency stability. So because earlier you have three, so you have three components. So you have a upper sideband, so you have a carrier, and also lower sideband. You have more component. So now you only have one component. So you already suppress the other two. So if any changes happen to the signal, so let's say some interference or changes in the data in the transmission. So when you receive, so let's say you are sending either. So when receive, it can become I word. So it can change. So the quality of signal get affected. So in order to prevent this effect, in these effects, so you need to have a better transmitter and receiver and frequency stability in both transmission and also receiving. Okay, so this some. So of course, if you see here, so more advantage than disadvantage. So whatever system that we have, it surely will have a plus and minus. So it depends on our application. So if our application, so we are focusing on reducing the power, we are focusing on increasing the efficiency, then we can consider SSBSC type of signal, okay, in our transmission. Okay, so with that, we conclude chapter 2. So summary of chapter 2. So we have divided into three parts. So part 1, we study on the modulation method. Classification is more on the terms, why we need modulations and amplitude modulation in general. Okay, so computing modulation index, so mu and percentage of modulation. Okay, bandwidth, what is bandwidth, how to calculate bandwidth, how to calculate power. So all these are we have seen in chapter one, part 1. Okay, part 1. Then in part 2, we have learned about AM modulators. So we have seen about square law modulators, switching modulators, and also demodulators, AM demodulators, square law demodulators, and loop detector. And today in part 3, so we have learned about double sideband full carriers, DSBFC, double sideband suppressed carrier, DSBSC. uh, so DSBSC, so we have seen two types of modulators. So balanced modulator and ring modulator. And earlier we have seen single sideband suppressed carrier. So all these three, it has different functions and different advantage and also disadvantages. Okay, so at the end, we have seen advantages and disadvantage of SSBSC. Okay, so with this, we conclude chapter 2. Okay, chapter 2. So, any question? Any questions before we finish? Okay, now 2:40. Anything want to ask?
No, that's it.
Okay.